Hello, everybody. Is this working? I assume it works. Good? Okay. All right, guys, we're going to get started. Thanks for everybody coming tonight, especially given that it's the first week of class. And, of course, this is the first lecture in a series of lectures that we will have not every Thursday, but pretty close. It'll taper off towards the end as you get busier within your studios. But this is the first one of the year. We also welcome people who are watching live online and also who join us later. Tonight I'm really excited to welcome Giuseppe Fallacara here at Lawrence Tech. I met Giuseppe last summer, is that right? I think it's last summer. It seems like forever ago because it was warm and in Italy and not cold and in Michigan. But I felt immediately after we met and I saw his work that he was somebody that I would love one day to invite to campus here to talk to students and faculty and to share his work. To give you some background, Giuseppe is a professor of architecture and design in the Department of Civil Engineering and Architecture at the Polytechnic of Bari, which is in southern Italy, where he teaches architectural design and stereotomy. And his research focuses on revisiting stone architecture with particular theoretical and practical attention to stereotomy. He has published journal articles, built full-size prototypes, and held workshops pertaining to the subject. He's the head of the New Fundamentals Research Group, a team of Italian architects and academics affiliated to the Polytechnic in Bari. He develops and research projects that deal with the relationship between innovation and tradition in architecture. And over the years, New Fundamentals has carried out research works on digital stereotomy, the history of construction, and sustainable housing in the Mediterranean area, and keeps its activities alive through teaching, learning, publishing textbooks, organizing lectures and workshops. They also supervise PhD dissertations and master's thesis projects. And I don't know if he has to work very hard to keep it alive, because I think anytime I look at Arc Daily or some other current thing looking at the topic of stereotomy, there is New Fundamentals Research Group, which is for good reason. So with that, Giuseppe, welcome, and we look forward to your talk.
Thank you so much. Good afternoon, ladies and gentlemen. And as you can see on the screen, our topic today is stereotomy, a very ancient discipline applied to the building construction, mainly in stone and wood, that appears interesting also for the current research. First of all, I apologize for my English. Sorry for my accent, sorry if you find something strange. I will read my communication and I hope everything will be clear. If you have any questions, do not hesitate to interrupt me. I first thanks very much Jim Stevens and the Dean of the College of Architecture and Design of Lawrence Technological University for inviting me and for the kind hospitality here in Detroit. Then I want to thank all the present for your patience and attention to my lecture. Synthesizing, I will show you a new idea of stone architecture. Architecture made by discrete, constructive, and compressed elements in perspective of stereotomy. My research on stereotomy started about 70 years ago with my PhD dissertation. The interest around stereotomy started to reawaken in the early 1990s with the research into the fields of history of construction. This new favorable cultural climate has allowed rediscovering the discipline, both for the historical value and the unexpressed design possibilities. The diffusion of 3D digital modeling and digital fabrication tools create an ideal condition to design and build a new object of architectural element of stereotomic design, characterized by considerable geometric complexity. Stereotomy is a know-how for constructive design, and for this reason, it is important to know its history, to preserve it, and to continue to spread it. Speculation about architectural form based on the use of stereotomy marked an historical relevant peak between the 16th through the 18th century, followed by a sudden break at the beginning of the 19th century. from the half of the 18th century as the result of a changed Weltanschauung world vision, classical stereotomy began to show undeniable signs of weakness. It was considered unable to produce anything but superfluous formal structure which failed to meet required needs. Blondel asserted that a good architect had to prefer verisimilitude naturalism to the pretension arrogance of stereotomy. On the other hand, is worth mentioning that in those very years, stereotomy was turned into a school subject, thus reinventing itself. This structuring was performed at the time in the École du Génie du Métier, one of the first military engineering schools in Europe, in French. From its establishment in 1748, before the coming of Gaspard Monge, the father of descriptive geometry, the teaching of stereotomy went behind the sheer utilitarian aspect of decline technique. The founder of the École du Génie du Métier explicitly specified, this art provides such an exact and accurate knowledge of the drawing of the plan and surface and the way of expressing the relief they propose to represent to be considered by the same standard as Euclid element. The École des Beaux-Arts and the École Polytechnique, representative of the field of architecture and engineering respectively, share from the beginning of the 19th century the common teaching of the subject of stereotomy, although they had specific curricula and teaching program. This subject was regarded as the most appropriate in encouraging students to build space and stimulate creativity. In those years, stereotomy became the pivotal subject in the first years of education of both the students of the École des Beaux-Arts and the polytechnicians. We know that the great 19th century architects studied stereotomy during their basic formation. Just to name some of the great ones, Eugène Viollet-le-Duc, Antoni Gaudí, Filippo d'Ernesto Basile, and many more. It's clear that this specific knowledge has pushed their project into innovative architectural realization. Right now, it is possible to think that the marvels of European, French, Spanish, and Portuguese stereotomic construction between the 16th and 19th century are only tied to the historical memory. Is it possible that the secret hidden within the magical vault of the City Hall of Arles are no longer applicable to the architecture today? Is it possible to believe that the technical knowledge of such vaulted spaces of European tradition, and in particular of the Mediterranean basin as a cradle of origin of stereotomy, has been lost to us? Is it possible to believe that the ancient language of stone architecture has been divorced from modern structural system and method of construction? I believe not. I believe, to the contrary, that the need to return to the study and construction of stereotomic vaults renewed by a modern architectural vocabulary that celebrates the materiality of stone is extreme importance today. This is my first true real experimentation, my home. This is a tribute to the ancient technique of the Apulian region, is the region where I live, and the technique of construction, this vault, is typical of my region and my limestone material, and is named Star Vault. I firmly support, and thus I want to underline here, the importance of reintroducing the study of stereotomic culture among the main basic teaching within the architecture and the engineering degree courses all over the world, as it was in the past. Here you can see some of my exercise that I made with my student of building construction 1, the second year at NYT this year are the little pavilion in the stone, thinking about some pavilion in Central Park. I emphasize that despite stereotomy has nowadays no large place whatsoever in both new building practice and structural plane of education, the subjects start to become a focal point of interesting high-level speculative research, not only the results of partial and isolated research in the riverbed of the history of construction. Just to name some of the great ones: Philip Bloch at ETH of Zurich, Brandon Clifford at MIT of Boston, José Palacios and Enrique Rabasa at ENSAB of Madrid, my group of research, New Fundamental Research Group, and why not Jim, Steven Experimentation. Why not? The aim of this research, I think, is to close the distance between practice and theory through the realization of some demonstration project. This stereotomic prototype describes an effort to demonstrate new application, feature, shape, and unexpected and unexpressed potential of stone or discrete construction method for a new contemporary design. The idea is to help the transfer and the spread newly appeared design technologies, educational method, and digital modeling supported by information technology in architecture. The continuous and rapid evolution of digital instrumentation for the conception and for finding in architecture has outlined the conflict between two terms, genotype and phenotype. The first refers to the genetic code of a form, and the second is the exterior aesthetic expression. Today, the attention of the designer seems to be more sensitive to the conception and construction of a genetic code than to the final aesthetic results. This is evident for the first time thanks to the digital tools that allow the design to conceive the form coding, which represent the mathematical and topological code of all possible formal variation on a single theme. However, I would like to draw attention to the phenotype, which is the precise object of the design goal, is the crystallized moment in which science becomes an aesthetic and artistic choice. The artistic phenotype, like a marble sculpture, is a condition that no code can ever fully conceive. It is the set of the cultural complex that needs to be researched and poetically sublimated. Is to be find the great masterpieces of the past and the attendance of great personality. The great man, says Gian Lorenzo Bernini, if they want, can considerably shorten the path who those who start. To the young, academy will give the rules of the art, but rarely and almost never the rules of the artist. Bernini says, we must follow three things: see, hear the great man, and practice them. It's important to note here that the most of the formal innovation and application, especially for the stone, derive from the knowledge and reflection of the architecture of the past. The study of ancient monuments makes it possible to understand the technical and building expertise and attempt to go further, following the famous phrase of Bernard Deschartres, who says that one could look farther by standing on the shoulders of the giants. Here we are on the Philibert Delorme, a great architect of French Renaissance, the father of the stereotomy, the treatise of the stereotomy. Here we are on the Philibert Delorme shoulders. The study of the past helps and trains us to the beauty. Here we are in the famous Chapelle d'Aneth in France, and we can see the transfer of this basic idea of the construction of the dome also in some other new construction in New York, the Swiss Bank and the Central Library. Let's go back to the conceptual basis of the discipline. If we observe the current research on the construction of the form or form-finding speculation, we can notice a great attention to the curved space and the vaulted pavilion. I'm sure that there is a constant and innate and perhaps unconscious desire to represent the celestial vault as the ancient idea of the sky at the basis of the design of the vaulted space of the secret classroom of monuments and cathedrals. I want to present here the bond that exists between the building of the ancient idea of the sky and stereotomy. I will try to demonstrate this fundamental relation between the stereotomy and the idea of the shape of the heavens by analyzing in detail the etymology of the word stereotomy. In particular, the term stereotomy in the architectural literature was used for the first time in 1644 in L'Examen des œuvres de Sieur des Arcs, written by Jacques Curabel, one of the most appreciated master mason. In his writing, the author examined and strongly criticized the previous text concerning the geometry applied to the stone cutting, written by Girard des Arcs, the father of prospective geometry. It's useful to note that the term stereotomy appeared here in the treatise of Curabel for the first time without the support and specific terminological description or etymological derivation. It was normally used to refer to the section of solid, probably deriving from the union of two Greek words, stereo equal solid and tomia equal cut. Here you can see some example through the portrait of Fra Luca Pracioli with a student, an example of the logic of the cutting stone. If you see in detail, the art of cutting stone, cutting solid using the water, in this case, give us the possibility to understand what is the shape that become after the cutting of stone. And so, thanks to these techniques, all the three basic techniques of stereotomy was born: tomomorphia, tomographia, and tomotechnia. One of the interesting questions is, how did Curabel, a simple mason, coined the Greek term stereotomy? If we try to investigate what geometry, earth measurement was in the Christian doctrine, we will arrive to discover an important conceptual link connecting to stereotomy. And well-known, a very ancient Christian representation of the world was ideated in the 6th century by Cosma Indico Peleuster. Thinking about the biblical tabernacle, Cosma, in his Christian topography, asserted that the cosmos was a rectangle with an arch covering the flat pavement of the earth. According to the Cosma's tabernacle model, the curved vault was hidden by the veil of the veil of the star events, called stereoma, or firmament in Latin, or the place where was located the fixed star, firm star, like solid star, motionless, adjective, not substantive. It's important to underline the strong etymological affinity between the terms stereotomy and stereoma, both derived from the Greek word astra, fixed star, and recalling somehow a vaulted space. The first one, stereotomy, referring to a real constructive dome, and the second one, or stereoma, the vault of perfect and geometric heavens. The only source of culture at that time, at the time of Curabel, derived exactly from the Christian precept through the biblical tradition written in Greek or in Latin. We can thus affirm that an important paradox takes place. The misinterpretation of the shape of the cosmos, the error of the flat earth, ecoumene, with the dome of the sky, has been at the basis of the realization of all the amazing architectural construction aiming to recall it. And so, the idea to build the vaulted space, it becomes to the misinterpretation of the shape of the heaven. We can have a lot of interpretation of this idea. The belief that the sky was made by perfect geometric shape, referring to the enlarged position of the fixed star, and according to the divine program, was challenged by Galileo Galilei. He clearly stated the demonstration of the random disposition of the star, opposed to the idea of celestial geometry, divine and perfect, gave the slant for a new approach to the study of the shape of the universe that no longer contemplate the fixity of Euclidean geometry, and give the birth to those who take the name of non-Euclidean and topological geometry, suitable for the description of the shape of the universe. In any case, the curved shape and the tessellation of the space are arguments in common both for stereotomy and for the interpretation of the universe. You can see an application of Harmonia Mundi of Kepler to the imagination of the conformation of the space of the universe. The vaulted space has always represented the ideal ambit in which to operate the more sophisticated and complex reflection, the construction of architecture. This is particularly true for stereotomic architecture. The curved shape with any mathematical complexity can be designed and built in two basic ways, with a tool that can draw the curve, for instance, complex or algorithm or code or mathematical code, or by operation of bending and deforming a simple basic shape. This is totally etude from the topological point of view. The idea of potential flexibility and digital manipulation of the lithic vaulted space is at the basis of the method that links topology to stereotomy. It's interesting to note that the term arch for the Latin arcus, is containing the term bending from the Latin plicare in a topological sense. Arcus and plicare, bend, is inside the word arcus. The idea starts from very simple consideration, that is the observation that most of the vaulted system can be imagined as a discontinuous structure like masonry wall that can be folded or deformed in order to obtain its geometrical final structural shape. For example, a stone wall can be theoretically bent to become a barrel vault, or going on to be bent and become annular one, and thus become a helicoidal barrel vault. The method becomes very interesting where more geometrical complex ashlar is block of stone, are considered instead of individual cubical block. At the end of the form finding and deformation process, the more complex ashlar, as assuming conformation that cannot be conceived through a canonical three-dimensional modeling. This method uses the technique of topological transformation thanks to software providing three-dimensional modeling and parametric variational one, thus basing on the topological geometry and is a function of deformation. As already stated, from a topological point of view, a plane and its rolled and deformed final shape are equivalent. Therefore, an homomorphism between the flat rectangle and the cylinder is given. If we proceed by virtual bending the cylinder, we can get a toric surface that is topologically equivalent to the cylinder and consequently to the rectangle of the beginning. By using some tools for 3D transformation and volumetric deformation of the shape, a correspondence between a flat surface and a spatial one is realized. The modeling process is thus considered as a flexible sculpture of three-dimensional digital data. Every single starting shape, maybe a parallelepiped or sphere or set of basic solid, can be modified by means of parametrical topological deformation to achieve the degree of complexity of the desired final object. This method was used by me and my group of research with excellent results during numerous and experience of new generation vaulted space, and for the production of expositive prototype and painture presenting during cultural events since 2005. Here you can see one of the first prototype in 2006 was the entrance gate of the Biennale of Architecture of Venice. It was very interesting because that was the final results of my PhD thesis. Is the entrance gates directly connected to the exposition City of Stone. And so you can imagine the first prototype realized in one important exposition. So a lot of people come outside this dome. And so there are no glue, no steel, it's only compressive vault. In this case, the object of topological manipulation have been referring to two well-known French patents belonging to the 1699 and known as flat vaults, voûte plate. And so I will show you the deformation of the original patent of the engineering, French engineering. In this case, we use the limestone of our region. The name is Pietra Leccese. One of this patent is one of the most interesting technical and stylistic speculation of the stone cutting, historically realized very few times. The first license patent considering this construction was ideated in the French by a French engineer named Joseph Abeille. The patent was published in 1699 in Machines et Inventions Approuvées par l'Académie Royale des Sciences in Paris. Here you can see the basic pattern was deformed in cylindrical way, and so deforming the flat pavement, the flat vault of the original patent, we passed from one unique block to using two different ashlar able to cover the entire entrance gaze. The static behavior of such solution is the same of a bidirectional slab floor structural system, working identically in both directions. Each of the ashlar is supported in such a way that the vault is working only after completion. Such static conditions allow us to consider such structure belonging to the structure called reciprocal frame structure. This was one of the first examples of stone reciprocal structure, because the reciprocal structure is normally made by wood construction. And so in this plan of the treatise of Fraisier, you can see the reference and the link between the reciprocal frame in stone and original reciprocal frame in wood. And so starting from this operation, starting from the study of this specific traditional ashlar, it's possible to invent new geometry and new conformation for the tessellation of the vault space, planar configuration, vertical or horizontal, cylindrical shape, and geodetical spherical geometry. Here is just a variation of the original patent of Abeille. And so in the first one you have a square geometry basic, and here we play with a hexagonal geometry. From mechanical point of view, this kind of vault is work after completion, after that all the blocks are assembled together. And here was some picture of the first experimentation that we made in France in the laboratoire of Ile d'Abo near to Lyon, to test for the first time the real resistance of this kind of vault. And I assure you that it's real, completely strongly and completely resistant. And so the idea was to imagine some variation starting from the planar configuration to the barrel vault and also to the spherical one, because the idea is to create also the geodesic vault using this kind of ashlar, this kind of pattern. And after this first experimentation, we have the chance to build really this dome for the first minister of the Qatar, Doha, and for his personal Turkish bath. And so that was some picture during the construction. And this is one of the pictures that I take during the construction. Here we have 8 meters of diameter of the dome, and I assure you that this kind of conformation with all these porosity and all these geometric shape are really similar to the sky, you know. And starting from this kind of observation, so only the logic of changing the shape, the basic shape, other project was made by other students of GSA of Paris, l'École de Paris-Malaquais. And so here we are in Jericho, and is the same technique using a triangular conformation. And so we start with my student to imagine different other composition. The portrait that you see here, the drawing is made from some exposition in Paris. And so focus the attention of the art of this technique, because I think that we can speak about art of the stereotomy, the art of cutting stone. So that's our other configuration that we work with the student during the third year project. And the idea is always to work in project, in design, and also in real demonstration, real realization. And so we work parallel in two ways, for a real constructive and for design speculation. And so we can finally we can organize, we can invent some new system of tessellation of the space using the logic of subdivision of the space and optimization of the geometry and the productive construction. Here, one of the last experimentation made with my group of research, the idea was to use two different material, black and white marble, in order to show the thickness and so the different kind of geometry that we can obtain cutting the stone using complex geometry. The latter is perhaps the most interesting. This one is the most interesting speculative configuration, and is representing the elegant approach ideated in 1704 by the Carmelite Jean Trouchet, also known as Father Sebastian Trouchet, to solve the problem of the pyramidal holes present in solution of a bay. Trouchet's solution was described in Mémoire concernant les voûtes plates in Recueil de l'Académie Royale des Sciences, toujours in Paris, always in Paris, in 1704. We use this unique technique and this interesting interlocked joint shape solution for many interesting structural experimentation during workshop with engineering and architectural students. Here was one of the most interesting experimentation. During one summer school in Madrid, in Spain, we realized a full-scale prototype of oblique bridge. And so with all the complexity, structural complexity of oblique bridge. And so you can see the deformation at the base of this structure using this kind of ashlar conformation. And so you can imagine that just to assemble this kind of vault, it's not possible to use the canonical, traditional formwork, but we invent two different formwork that they move horizontally just to create the anchoring, because it's not possible to put the last keystone from a vertical position. And so, according to the canonical engineering point of view, this vault cannot be cannot be resisted to the form. But after using this kind of geometry, we have make the demonstration of the possibility of the reduction of the thickness and also the angle of oblique of this bridge. Here you can see other different kind of experimentation, also the shape, in the Möbius shape, using this kind of conformation we made in Melbourne University, just an arch that proves exactly that also if we twist this kind of arch, thanks to this kind of connection, the ashlar and the arch will work very, very well. And so our interest in this solution lays on the one hand, on the capacity of a structural system to provide an infinite formal generalization. On the other hand, on the bone shape logic, the shape of the bone's connection, among the connecting surface of the ashlar. The osteomorphic design is optimizing the mechanical performance of the vaulted system, improving the transfer of the pressure between the ashlar. And so it's not only a aesthetical condition, but it's also a mechanical condition to improving the mechanical behavior of such voltage spaces. And we make another kind of experimentation using the marble and the osteomorphic connection of the joint to realize one catenary arc, pre-stressed catenary arc, and presenting during an exposition, the most important exposition of the marble construction in Marmomac in Verona. And so you can see the form of the catenary arch with using this ashlar, this block, with osteomorphic condition. And this kind of operation, there is a strong morphological affinity between the block that you can see here, of the block of Truchet, and the block and the recent research of a research group of Professor Yuri Estrin of Monash University in Australia. And so a new family of stereotomic vaults set out from the typical interlocking of the ashlar of the flat one can be formalized by using the deformation by folding technique already exposed. This perspective aims to solve some of the most important theoretical issues related to the realization of voltage spacing, improving mutual anchorage and therefore the friction among the ashlar of the voltage system, reducing the wall thickness, designing subabbreviation ashlar of the vault both as ornamental and so aesthetical and structural behavior, varying the shape of the vault system in a particular parametrically way, automatically obtain all the geometric data both for the manual and electronic cutting CAD, CAM, CNC, and of each individual block, automatically provide all the numerical data aimed to the structural analysis, and rationalize the number of standard ashlar for the construction of many complex voltage structure. This last idea is very important. The interest in this kind of research is to try to achieve a complex voltage structure with the smallest number of standard ashlar in order to optimize the constructive process. In this specific idea, we have invented a system that optimizes both the reduction of stone waste during the cutting, speedy manufacturing, and the use of only 2 ashlar geometry to build a complex spatial shape. The system is called architectural hyper system and is based on the geometry of hyper ruled surface that can be cut using diamond wire cutting robot. And so you can see that thanks to only 2 geometry, one specular to the other one, you can build different kind of geometrical shape. And the idea is to use the diamond cutting, wire cutting robot to cut all the block, all the hyper ashlar, all the hyper block, starting from one unique block, parallelepiped block, and without the creation of the waste. And so you can see here that starting from only one block, we can cut, because they are ruled surface, and so we can use the robot cutting, we can cut all the ashlar, and we can also store in a very easy way. And thanks to this geometry, we can make a lot of configuration using, I repeat, only 2 geometries, not a lot of geometries. That's very important, because for the improving of the construction building of this kind of a prototype, it's very complex if we have a lot of different kind of geometry. That's the difference between one and the other. One is just little millimeter or angle. And so we can have a straight wall, we can with the same geometry, we can build a straight wall or a sinusoidal wall, and we can assemble in very easy way. That was the first prototype that we tried to assemble. Here we are in Verona, in Italy, in the Marmomac, for the exposition of this the first year was inside to the exposition room of the Marmormark, and the second year was, and this year was outside. I prefer the installation outside, obviously. And if we try to continue to imagine some other configuration using this kind of ashlar, finally we arrive also to the idea that we can create a barrel vault using the same two geometry. And finally we built this year in Troyes, the city of Troyes in French, this first prototype of porous barrel vault using only two geometry. And so the technique is always the same. We start from the frame, using the framework, and after we start to assemble every block. And in this case, the interesting is that if you imagine the center of the hyper block is a line. And so we cannot really see immediately that you have a line inside here. And so because there is a line, the junction of every line inside of each block is the position of the cable for the pre-stressing, post-tensioning cable. And so the structure is pre-stressed structure. And you can imagine that we have just an arch line inside to the center of each block. And here at the base, we have the position to make the post-tensioning of the structure. And so you can see the parabole, you can see the hyperbole, you can see if you have the capacity to see the cutting of the wire cutting machine, you can see the line. So you can see all the geometry inside these vaulted spaces. And it's I repeat, this barrel vault is lightweight, is porous, is aerial, according to the teaching of my master, is Philibert Delorme. Philibert Delorme affirmed that the architectural production based on the use of stereotomy has been constantly focused on the game of paradox that could ensure a heavy stonework and in the same time seems to be an aerial structure. He says, suspendu dans l'air, airborne. In this regard, the celebrated vaulted realized in Château d'Aneth are paradigmatic. This is the central focus of my PhD dissertation. The trompe d'Aneth is one of the paradigm of the stereotomy described inside the Treatise of Architecture in 1567 of Philibert Delorme, the first treatise of architecture, the French first architectural treatise. And despite the heaviness of the stone, such architecture must defy gravity, sending dynamic and antistatic ones, derived from the ethereal sky. The dialectic contamination between the heaviness of the stone and the lightness of aerial and pneumatic form of the starry sky, stereoma or firmament, is the main lever of my research. For many years now, I've been investigating the morphological potential inherent in this assumption as a conceptual foundation for the updating of stereotomy and stereotomic design. As mentioned, the paradox is a constant in the logic of the stereotomic design, descending to a formal lightness starting from an opposite material condition. The first poetic paradox of stereotomy was described by Charles Perrault in what I consider the best definition of the intrinsic meaning of the term. The stereotomy is the art of using the weight of the stone to enhance the lightness of the form, describing the combination between weight versus lightness in the same architectural vaulted system. And the definition is very interesting for the people who knows the French. The stereotomy c'est l'art de se servir de la pierre contre elle-même, de la faire se tenir en l'air par le même poids qui la fait tomber. I give you these sentences just to push you to translate it. It's very poetical. And with one of my recent stereotomic achievements, I think I have completely interpreted the concepts of suspension and lightness according to the teaching of my maestro Philibert Delorme. I'm hanging on the here on the yard crane. I assure you that is not a photo montage, and because that was one of my last and it is present of the poster on the poster. This is one of the last construction that I made in Troyes in France. Is the first hyper made in stone, in pre-stressed stone. And so you know there are a lot of hyper built during the modern period in concrete, but that's the first in stone. And so I'm very interested. I'm very happy to have realized this kind of structure that is, I assure you, is very, very complex for the construction and also for the computation. And so because the stone are no glue, they are not glued together. Because of the hyper condition, you can find a straight line inside the joint of the ashlar. And so you can put inside a pre-stressed bar cable, and thanks to this condition, the structure works very, very well. And also in this kind of construction, because it's not in concrete that you make the formwork and after the concrete, but you build directly with the pre-worked perfect geometry, you have to be very put a lot of attention during the assembly. And the stone looks like flying in the air. And flying in the air, I put this image, you can find a lot of things, and these two guys find the love because he was proud to make the declaration to the fiancé, you know. And we arrived just at the end. At the end of my presentation, I will take you a few minutes of your kind attention. I would like to present the 4 research topics we are currently developing with my research group, New Fundamental Research Group, and with the various companies of the world of the stone. One of the first ideas that we developed in the Puglia, in the south of Italy, is company inquiry. We built a very big company directly inside the quarry. And so here is the first example that we want to do that. The first example of a very big company, but not traditional one, because it's completely robotic company. And so all the best robotic situation will be located inside the quarry. And so if you come in Italy, you are welcome to see this kind of experimentation. So the company is inside the site of production. The second is the company that built itself. And so the know-how of the company allows to create their own building. This was a building built in French, in Troyes, the region of the Champagne. And so if you are visiting in France, in the region of Champagne, you are welcome to see this experimentation. It's a company made by 4 big arches without any glue, without nothing, and every arch was built in 1 day because we use some specific way to optimize the mounting of the big arch. It's 20 meters arch, and the same company. With the same company, we invent this new system of construction without using of the centering, presenting in the last Salon de la Pierre in Lyon. And so the idea was, it's possible to build vaulted system in only one day, because this kind of operation take a lot of time for the mounting. And so we proved with using this system that in only one day we can build a very big, for the stone construction, pavilion, using this technique of pre-anchorage of the joint, and using this kind of metallic system just to fix during the mounting. So here you have some picture during the assembly in the day before the exposition, because during the exposition the pavilion are made in wood, in something very quickly, never in stone. So we proved that also with the stone we can be very rapid during the construction. Another kind of research, very interesting, is the combination of the carbon fiber and glass fiber with the stone. And so here we have some furniture presenting during some exposition using this technique. This is a stone from Sicily, very beautiful stone, and carbon fiber. And so you can see the thickness of the stone, and without this combination it's quite impossible to have the resistance of this kind of material. And so also for some installation, double, very thin, here we have 4 millimeters of double stone with glass fiber inside. And also some furniture is the last marble we present, a table with 1 centimeter of marble and carbon fiber. And finally, we are working with CoAD, CoAD group, for the using of this kind of cladding stone in 3 millimeters in granite and carbon fiber and glass fiber. And for the first time, if you see the granite is 2 millimeters of granite, the panels are very are big. For the first time, the granite, you can see the light inside. And so these are some picture of the technique of the working of the stone, and the connection that we use is with magnet connection. Here is the project that I developed here with the student of NYIT for the new building of health profession. The new school of health profession is one half plane surface with using this kind of panel of carbon fiber and granite, very thin granite, 3 millimeters of panel. And another research that we do is the pre-breaked stone using the west of the stone. So all the west of the stone, the very thin marble that we normally we don't use, we can pre-break, make the pre-fracturation of the stone, and we can create an I don't know the term, the limon is the helicoidal structure for a staircase. And the last research is the using of the waste material, the waste material of the work of the stone to be transformed in filament or in mortar for the 3D printer. And so we are working about that with the company, Italian company, the WASP, for the creating of dome structure using the mortar that use all the waste of the stone working. And that is one of the last idea, utopic idea, to build some tower, very tall, using some robotic 3D printer, if you want, with additive manufacturing, thanks to this kind of geometry that allow to the stratification during the construction. And so that's, I assure you, is my last slide. Finally, returning to the didactic point of view, the idea is to create a new expanding architect with robotic arts ad auctus architectus novus, who speaks the language of technology and the Greek and Latin of our origin, like stereotomy tried to teach us. Thank you very much for your attention.
Do we have any questions? Hang on, I'm going to hand you this because the live stream wants to hear you.
I hope everything was clear.
My biggest question is, what do you find most compelling about stone?
What's sorry?
What do you find the most compelling about cutting stone?
The difficulty? What's the
most compelling part? Like, what do you enjoy the most of cutting stone and the material?
I don't know if what's the...
Like, what's your, in terms of stone, what do you find the most interesting about the material specifically?
Wow. The stone is, I will tell you something. The stone, a lot of people think that the stone is an ancient material, But as my teacher says, there are no ancient material or modern material, but it's the way to use the material that create a new architecture or ancient architecture. So I think that, yes, it's important to do new research or new material, but the stone, according to my opinion and the experience that I have, is the best material to build architecture. Because also after 100 years, 1,000 years, it's become beautiful and beautiful, The other material has not this capacity. And so for me, I think for every architect, make one building in stone will be the most interesting in the life, because the stone will survive after you, And so that's why you will be, the memory of you will stay there. And I think that I'm romantic, but I think that that's the best idea of stone.
Fascinating research. My question is, first of all, it sounds like modularity is a key factor in your research, right? So my question is about the process. How much does the form that you come up with is the result of interactions between those modules which create the final form? Mm-hmm. Or how much does the design form kind of imposes the configuration of modules?
Yeah, exactly. If we talk about stereotomy, we talk about discrete element, and so we cannot talk about continued element. It's discrete, and so discrete element is modular elements, and so you can have a strict relation between the final shape, and the modular shape. Because stereotomy is beauty because the global shape are complex, and also the shape of each ashlar are complex. And so you can work in both ways, starting from the module and arrive to global shape, and to the contrary. And when you work in stereotomy, every time you pass from one side to the other side continually, from the global shape and the modularity. At the end, I don't know if I answered to your question, but there are not one time you say, okay, now I start from this shape. It's continually in variation in your mind, starting from the global shape to the single ashlar. And I think that the stereotomic design is continuing the variation between these two parts, the global and the particular, the global and particular. So, but from a constructive point of view, I think that if you are able to find a family of few blocks in order to give you a more complexity shape, is more smart idea to build the stereotomic architecture. Because I think that it's very easy, but today is not that's the consideration. It's very easy to make a complex architecture with a very complex number of ashlar. The difficulty is not that. The difficulty is exactly the contrary. Are I able to do a complex shape using only 2, 3, 4 ashlar? But today is exactly the contrary, because the people, I make a good job with 300 million of block. Okay, and now what's the interesting about 3 million of block? Is that the computer give you 3 million block, and it give you exactly in the good way to put. But after the people that are in the area of building, they become crazy to. And so what's the smartest in this? If you are able to do a complex shape, an interesting shape with a very few modules, that is interesting. And so when you work in the stereotomic way, you have to think about that. You have to think that in the building area, there are some people that will be able to assemble in very easy way your work. I don't know if...
No, yeah. Any other questions? Yeah.
I hope that after this suggestion, in this school, some project in stone will be made.
Is this on?
Yeah, it's just online.
Oh, okay.
Speak into it. Yeah, just speak up.
So you covered a lot of factors of the subject of stereotomy, like the etymology of the word itself, and then the Greeks' interpretation that the domes were a translation of the sky, and Philip de Lorenz, his trait drawings, and all those. I'm wondering which factor of the subject sparked your initial interest, and where you developed like your conceptual grounds for what, the rest of your research.
What's my...
Yeah, what was your first like conceptual interest? Yeah.
Yeah, all that I show you was made by the research that I start. I will tell you about all the history about stereotomy starts 20 years ago with the researcher that made, from historical point of view, the research about the birth of geometry, descriptive geometry, or the birth of projective geometry. It was a study linked to the fields of geometric design. Nobody started with the idea that it's at the base of the stereotomy, that the stereotomy is a tool to build, to make the architecture. And so I start with this new idea that stereotomy is a way to make architecture, new architecture, because that was in the history of structure, of the architecture. And I think that during this process, I was attracted from the study of the origin of the term, because I thought that this kind of technique we cannot imagine only like technical operation, but I think that there is a philosophical, and so for this reason, I study and I found this relation between the stereotomy, the term, Greek term, and the stereoma, that is the term that in ancient period was the sky. And for me was shocked because the terms are the same. And during that period, Courabelle in French, he certainly doesn't speak Greek because he was a master mason. I say, but how he invent these kind of terms there? And so, because the only cultural base was the Christian doctrine, the Bible test was in Greek and Latin, only in this test you can find this term, stereoma. But stereoma is the sky. Yeah. And so the idea is not to cut the stone, one solid, but is the cut of the sky, the cutting of the sky. That's the idea. Yeah. Because it's complex, but if we try to analyze also Pythagorean and Platonic way, the question is, what is the geometry of the sky? the sky is ethereal, there are no shape. And so they start to invent the composition of the atom of the sky, in the same logic of the cutting stone to compose the dome. And so the questions are the same. And so what I mean, in my background, I have more organic vision. And so I want to see all the point of view of one topic, not only one focalization. Otherwise, we don't understand what is the sense of our work if we don't understand everything. Philosophical point of view, etymological point of view, every aspect, technical, engineeristic, and so on, not only practical. You know, for this reason, I told to my student, when you think about stereotomic design, you have to think to the heaven, not to think what shape I can do with this kind of geometrical computer operation. You have to think about the sky, you know, because that was at the origin of everything. Because the people imagined that the sky was with this form, you know. And so that misinterpretation was at the base of all the conformation of the church, of the big, room, because they want to represent the sky with the fixed star, because they imagined that was geometrically linked, and so perfectly linked. And so Galileo Galilei says, no, it's not like this, but that's another history. And so I feel that this topic must be taken in a global way, in an organic way, you know. Thank you.
Any other questions?
So I do have one question, and it's just and you kind of just referred to it a little bit, but since the nature of the arch has been, rooted in mathematics as to how to execute this and actually build it, even if the inspiration was driven from looking to the stars, how have you seen the influence of software and technology impact this? So let's say if you do have some type of an idea for a design and you try to reach that, how do you feel the software is allowing you to reach those goals, and do you see room for improvement in the execution of these forms?
Yeah, thank you. This I will say something. At the beginning, stereotomy was a secret knowledge, only for the people who take part of a group, a secret group of Masons. Like the name in French is Compagnons du Devoir, a congregation of tailleurs de pierre, congregation of people that cutting stone. And so it was very, very difficult to spread to everybody. So the people that at that time was able to do some construction in stereotomy was very few people. And so after, with the birth of projective geometry, and so thanks to Girard Desargues, that was not stone mason, but was a geometry, was not inside this congregation. At this moment start the work between the congregation of the knowledge and the geometry that are able to spread this. And so between Girard Desargues and Courabelle, there was a very, very hard work. And so why I tell you about that? Because if something is very hard, automatically the art will die. If you have the old language very difficult, they not survive because they are very hard. Thanks to the technological and the 3D modeling, thanks to these new tools, the stereotomy was carried out and has now a new life. Otherwise, without the 3D-dimensional software, it's very, very difficult to build something, to understand something that needs a lot of projection, I don't know if here you made the projective geometry manually or descriptive geometry. For instance, the descriptive geometry, you know, when I talk about descriptive geometry, is one of the basic topic and matter in all the school in Europe. You start with descriptive geometry, with the intersection of solid, but only by hand, without computer, you know.
I do have a question, though. Have you ever worked with any computer scientists or anything at a university just for like the advancement of the actual computation itself, like utilizing the power of computers to like maybe generate certain geometries that we couldn't even think about?
We work a lot with the computer and the program of generating, you know, parametric geometry. But the problem is that our way is we have a lot of limitation because the stone working only a compression, because the material, and so the material you cannot cut some angle because naturally it's broken. A lot of, and so this kind of research on form finding and geometrical shape is not free, you know. We have a lot of limitation with the stone, and so it's very hard to find new improving and new shape. But it's the work that we do now with also with the young collaborator, you know, that you are able to use a very complex software, but it's always linked to the stonemason. When we make something, we speak with the stonemason every time, because if something is not possible to do, we cannot make only speculation. You know, the speculation is interesting, but we have to prove that it's possible to do.
Thank you.
I hope to.
Yeah, Giuseppe, I'm going to ask a question only. I would normally do it last, but I think because it fits to what you just said. I was lucky enough to speak to your mason. And he talked to me a little bit about the tolerance of the stones when they come out of the robotic cutting. And I was wondering if you could speak a little bit about how important he is in terms of the success of the projects and how that maybe ties back to how this technique was originally a mason's knowledge to begin with, right? But I mean, one thing he said to me is not uncommon to have a millimeter that he has to hand modify the computer cut block. But that substantially changes the labor model, but also raises the stakes on having highly skilled masons, which is an interesting phenomenon.
Yeah, I will say when we create the final executive model just to make the production, for us the joint is always 1 centimeter, always. So we don't create the tree model with the 0 joint, you know. It's impossible because the tolerance is very important. Otherwise, we cannot. And so now we have the expertise, and so what we cut is perfect to be built, you know, after a lot of experimentation. But when we think about the 0 joint thickness, it doesn't exist. We have always to preserve the joint during the fabrication. And the other question is, it's not very easy to understand the world of the stone because it's very complex. Because the stone arrives from a quarry, and the quarry is normally a sedimentation, you know. And so, because we use the limestone, so we have the layer of natural sedimentation. And so the stone arrive cutting from the quarry, but this layer of sedimentation will be always perpendicular to the direction of the pressure of the stone. And so we cannot put inside the block the ashlar in what we want, but in a specific position, because we cannot put, for instance, the direction of the ashlar in a parallel way of the direction. Exactly. And so this is one of the first limitations that create the difference between other material, artificial, homogeneous material that we can cut, and stone. Because the stone, we have to respect the nature and the best performance of. And so it's complicated the way. And sometimes, and also during the history, you can lose a lot of material just to carry out, the block that you need in the perfect way of the direction of the pressure. Okay, and so sometimes you lost a lot of material, but you cannot do nothing. But the idea is the recuperation of this material to create a new life of stone with the 3D printer, what I showed in the last slide.
Any last questions? All right. Well, thank you very much. Giuseppe.
In any case, I want to say the last. I'm organized a symposium, Stereotomy 2.0 in NYIT, the April 20. And so I will give you some information. If someone will come, I will make an exposition in par excellence a gallery of art in New York, in Manhattan, with some interesting visiting is Shejay of CoAD, the director of CoAD, Act 2. And so we will do something interesting. If we want to make some exposition, if you are interested, I will send you some reference.
Right?
Thank you.
All right, thank you, Giuseppe.
Thank you so much for your, and sorry for my terrible English.